Hi there, it's nice to have you back for our next step in our discussion of PostgreSQL buffering. We need to add one thing to the mix to make our discussion of PostgreSQL buffering complete for now. And that's a strategy that is being invoked whenever the space in the buffer is really scarce. When we are forced to pick a victim and remove that victim page from the buffer because some new fresh content has to be brought in. The buffer is a limited resource. We only can use 128 megabytes or only 25% of the actual RAM, maybe even a bit more, maybe even significantly less of RAM to hold pages in the buffer. And there will come a time when there are more requests for pages than actually available slots or space for pages inside the buffer, and then it's as time has come to pick a victim. How should we go about this? This video is about this particular process of picking a victim. So whenever we perform read buffer, then we need to pick a buffer slot, of course, because a new page has to be brought in. A new page that we assume is not already present in the buffer. Otherwise, everything is fine, and we are in the easy case, in the hit case, above the dashed line, and everything is okay. So let's assume we enter the region below the dashed line. We had a buffer miss, and we now need to act. We need to find a free space, free space V, let's call it, inside the buffer. The buffer logic internally in PostgreSQL has a list, a free list, it's called, of buffer slots that are guaranteed free, that are available for the allocation of new pages. Okay, and if that free list indeed is non-empty and has some pages to spare, then that's fine. We will, from this free list of pages, we will pick some page V and return this as the result of our read buffer call. So that would be the easy case where there has still be some slack space, some space inside the buffer. So buffer slots are appended or added to this free list whenever it's obvious that that a page inside the buffer is not really needed anymore. That's the case, for example, when the database server or the buffer manager restarts. Everything starts afresh, then all of the pages of the buffer should be found on the free list. Because there's no available or valid content inside the buffer, all pages would be in the free list, and we could just pick from that free list any page that we need. Sometimes there is really major disruptions in the database or table states. For example, when an entire database is dropped, or even if only a single table is dropped, then all of the contents of that database, all pages relating to that database, or all pages relating to a particular table, are obviously not needed inside the buffer, and the allocated pages inside the buffer would go onto the free list. And from that list, we would first try to serve a free page V. If that free list is empty, and that means that the buffer is not aware of any guaranteed free pages inside its space, then we have to go and hunt for a page inside the buffer that could be a possible victim. A victim to replace right now, because we have to bring in fresh contents from secondary memory. We need a buffer replacement policy that picks a particular page V inside the buffer, declares it a victim, removes it, and frees its slot for some fresh new content that can be brought in. So that buffer replacement policy would be tasked with picking one of these pages V, and we would pick this page V and return it to the caller, probably paying some cost to remove that victim from the buffer. Okay, these two cases, the free list is non-empty, good case, or free list is empty, bad case, we have to pick the victim, have been marked with 1 and 2 in the skeleton or in the sketch code for the read buffer routine. So if you flip back a few slides, you will see these marks 1 and 2 that relate to the discussion on page 14 here. Okay. So what could be a possible replacement policy? There are many, actually, and we will mention a few here, but we will look at one particular policy a bit more closely because it's very widely spread and very widely implemented, and it's also the policy that's currently in use inside PostgreSQL. And it's called the least recently used policy, or the LRU policy. All right, so the page V that has been least recently used, whose usage lies in the past, really lies way more in the past than any other page. This would be the least recently used page, and it will be the victim. We just assume that V hasn't been used for such a long time, then it's not very probable that V will be important in the near future and will then be used. Okay, a page that has been least recently used will probably remain unused from now on, and it could be a potential and good victim. So we could decide to maintain a data structure that keeps track of all the least recently used timestamps for each of the buffer slots inside our buffer, and we would need to update these timestamps and then probably rearrange and resort the data structure so that the pages with the least recently used entries are easily found in that structure. But there's a trick that one can play, and it's a very clever arrangement of pages or of buffer descriptors for these pages inside a very simple data structure in a circular list, namely, that can simulate the behavior of least recently used. It comes close to least recently used and almost acts like an LRU strategy, and that's the clock sweep algorithm, or the clock sweep strategy. Okay, so let's have a brief look at that. So what we would do is to arrange all the buffer descriptors inside our buffer space. So if you recall, we had 16,384 pages inside a default PostgreSQL buffer. All of these 16K entries would be put into a circular array, or the clock as it is called in the context of the clock sweep algorithm. So we would have an array of these many entries. Let's just call this large number of entries, let's call it N here, capital N. So the N buffer descriptors would all be held in a circular array. Circular array means if this would be the array, and we would have some index wandering through the array. If the index reaches the end of the array, we would just start at the beginning again. So that pointer would just rotate around the array. This is what makes the array circular in a sense. And that pointer in the context of clock sweep is called the next victim pointer. The next victim pointer points at the buffer descriptor that we intend to pick as the next victim. You are the unlucky, the sad page that will probably be picked when we are in dire need of some free space inside our buffer. And we will see how we cleverly and correctly handle this next victim pointer inside the clock sweep algorithm. But this could be the potential victim, one of these data buffer descriptors currently pointed at here. A buffer descriptor has some interesting entries here. There are some entries that we won't detail, but there is two bits of the buffer descriptor metadata that we want to highlight here. It's the ref count. So how many operations inside the database systems are actually looking at this particular buffer right now. And it would be 0 for this particular buffer descriptor. So that would be an unpinned page in a sense. Nobody is currently interested in the page. And the usage counter, which is the abstract measure of value. So how valuable is this page? How often has it been used recently? And a value of 3 indicates that 3 such uses have been happened recently. That's more than only these 2 uses of the neighboring page. So the value of this buffer or its descriptor would be considered higher than this of its 2 neighbors here. All right. As I told you, the maximum number of this usage count value is 5 in the default installation of PostgreSQL. It's not really a usage count; it's an abstract value measure for the current value of this page. Okay, so that would be all of the data structure that we are needing. And as I told you, we will just move this circular pointer around the array, which is super efficient and super easy and simple to implement. So let's see how this clock sweeping algorithm would look like. We would need to find a victim page. If you recall the pseudocode for the read buffer operation, in the read buffer operation we were calling just this particular version, this particular routine to identify a victim page. And now finally the time has come where we can look inside the internals of this particular routine. Okay, so we will have to try hard to find the victim page in the scarce space of our buffer. And there's a try counter here that will make sure that we are not looking indefinitely for such a victim page. If we cannot find one after this counter, if you cannot find one after a certain number of iterations of this loop that we were going to enter next, if you cannot find a suitable victim, then we will give up. We cannot find a particular victim, we still need more space, then we have to signal to the rest of the system that we are actually out of buffer space. We need more space, we cannot find a particular victim. This is a situation where it would be time for the database administrator to consider to really enlarge buffer space or reduce workload on the system, because we just cannot handle the read or write the number of read or written pages with the buffer of the current size. It's just not possible right now. Okay, so let's assume that there are still some attempts, some tries left to find a current victim page. So our first guess would be, we would look at the circular array at the next victim pointer, and that should be our potential victim V, okay? If the ref count of the victim V is not 0, then there is some operation inside the database system that currently relies on this page V, okay? So this cannot potentially be a victim. This cannot potentially be a victim, and we would be out of luck here. V is pointed at by next victim, but it cannot be currently a victim because somebody else is relying on that. Okay, so that would be this particular if condition, and if this is not fulfilled, we would enter this else branch, which would just say, hey, we made one attempt, we made one try, this failed, okay, so let's record that we made this attempt, and then move the victim pointer further in circular fashion. As you can see, we would just increase the next victim pointer, but would make sure that we wrap around when we hit the array end and start at the very beginning of the array again. Okay, so then it would be time to have another try if we are still allowed. Okay, so the next page, the next potential victim would be found, would be identified, and now let's assume that its ref counter is indeed 0. There is currently no current operation that is relying on this particular page. The page is not pinned, the page is unpinned, and it would indeed constitute a potential victim. Before we pick it as a victim, let's consider its usage counter, its abstract value measure. Okay, and use that value measure to see whether this indeed should be the victim. We would just use the current value, the usage count measure of this page, and decrease it by 1. If the usage counter has been so low that the usage count has now reached 0, then it's time to declare V the victim and return it as the potential victim. Okay. If the usage count has been higher and a single decrement of its usage counter has not brought the usage counter and the value of the page down to 0, then maybe the value of the page has been rather high. Maybe it's better to go on looking for for another victim inside the buffer that has less value. Okay, since we decremented the usage count at this particular point, we will remember, or the next time we will come around this particular page, its usage count will have been decremented. Okay, if nobody else has incremented its usage counter in the meantime, this might happen asynchronously as this note says, then the value of this page has been reduced, and maybe at some point it will come down to 0, which will then be the point in time where we pick it as a victim. Nobody has declared interest or has used the page in the meantime. Its usage has gone down, so it's time to remove this particular page. We reset the try counter to 0 here because the situation inside the circular clock array has indeed been changed. It has indeed changed because we have decremented the usage counter and made some progress towards the picking of a victim. So page V is now more probable to be picked as a victim on the next sweep, on the next circular round of the next victim pointer through the array. So that would be the clock sweep implementation. Let's see in a tiny example how that could look like. So if this would be our circular array of capital 9 equals 9 entries in this particular case, then we would first consider the buffer descriptor pointed at by next victim as one potential victim to replace on the next call of our replacement policy. We would inspect its buffer descriptor and also see that its ref count is not 0. Somebody is currently relying on the presence of this particular page inside the buffer. This cannot be a victim. This cannot be a victim. This one will keep us from picking this particular page as a victim. So the page is pinned. We have to skip and consider the next page, the adjacent page in the circular array, as one potential victim. Okay, this would be this step. Indeed, this page has a ref count of 0. A ref count of 0 indicates that currently nobody is interested in this particular page. It could indeed be a potential victim, but its usage counter has been 2, so there has been some interest in this page, and maybe in the near future, interest for this page might revive. So maybe it's not the best point in time now to pick this particular page. Maybe we can find an unpinned page in the vicinity that has a value so low that the decrementation of this usage counter would bring it down to 0. A decrementation of the 2 brings it down to 1 only. That's not 0. So this buffer descriptor gets a second chance in a sense. So we would move on still. But the next time when we are parsing with our next victim pointer, the value of this page will be 1 only. And so this page is now in danger of being picked the victim on the next round through the circular array. But for now, this page is safe. So let's move on with our victim pointer. We find an unpinned page indeed. Its usage count has been 1. We decrement this to 0. This is a page that's not currently being used. Its value is, its usage count is 0 now. So nobody has shown interest recently in this particular page. This should be the victim. We pick this victim, this page as a victim, and we will report its buffer descriptor as being the victim page. And the next IO operation from secondary memory will replace this particular page. Okay. So LRU appears to make sense, especially under the assumption that pages that have been least recently used are not being used in the near future. Interest for these pages has been waned, has been dying out, and we are not expecting interest to rise again in the near future. You are the victim. That's the heuristics, the thinking, the assumptions behind LRU. This works well in many cases, but there are some challenges for our LRU. There are some scenarios, not so uncommon scenarios in database operation, that could put a question mark on LRU. There are some situations in which LRU maybe picks unlucky victims or doesn't make the luckiest of choices. So let's look at 2 of such potential scenarios here. These would be challenges for LRU. So consider a scenario where there are 2 data structure involved, a relation of 10,000 pages. Okay, so a relation of 10,000 pages, a table of 10,000 pages, and an associated index structure for that relation. And as is normally for such index structures, they are really considerably smaller than the tables themselves. So in this particular case, in this sample scenario, the index structure for table R is 100 times smaller than the table itself. It only has 100 pages. What we will now observe when we look at the operation of the database system is a typical usage pattern. A usage pattern that accesses a page of the index. The index will then point us to a page inside the table, which we will then access. The next lookup will start in the index, which will point us inside the table before the next lookup will hit the table, and then the relation again, and so on and so on. So we will have a back and forth between the index and the relation, the index and the relation, the index and the relation. This will be the page access pattern, as we call it, the page pattern access string, IR, IR, IR. Okay, so how will an LRU operated buffer cache operate in such a scenario? LRU operated buffer cache of, let's say, only 100 slots. LRU will lead the system to keep the most recently indexed and table pages inside the LRU buffer. The most recently used index and LRU and table pages will be in the buffer. So 50 of the slots will be occupied by the index pages, 50 of the slots will be occupied by the table pages inside such an LRU operated buffer. And that's not the wisest of choices, because the probability of reusing one of these index pages, there are only 100 of these, and the probability of reusing one of the R of the table pages, there are 10,000 of these, that is 100 more. The probability of the reusability of one of these index pages is by a factor of 100 times higher than those of the table pages of table R. Okay, so the scarce resource of the LRU buffer should probably be invested in caching these index pages only, because they have such a high probability of being reused again, and their presence in the buffer will save us from reloading these pages of the index from secondary storage. The probability that we are hitting a table page twice is by a factor of 100 smaller. Okay. So LRU will only consider the least recently used pattern and will keep I and R pages inside the LRU buffer in an equal measure, while it might be more wise to invest that space in the more frequently hit index pages. Okay, that would be one scenario where LRU of course works, but could behave more cleverly. Okay. Another scenario might be where a number of transactions, a sequence of database operations, really focus on a very small fragment, on the same small fragment of the database. This would be the hotspot of the database, and would be very valuable to hold the pages of this hotspot inside the LRU buffer cache. Okay, so all of these transactions would benefit from this. The value of these pages should be really high. But then another transaction, another sequence of operation comes by, T0, and that operation would just perform a sequential scan of a very large table. Think of a SQL operation like this. So a table with really lots and lots of rows, 100 million rows, all of which are maybe even wide, containing text data and so on. So lots of pages are needed to hold the contents of this really large table. This sequential scan of the table will bring in all of these pages, and these pages will only be used once, but they have to be brought inside the database buffer to be available to the sequential scan. Okay, the value of these pages would be way less than the value of these very regarded hot pages that are read by the other transaction T1, T2, and so on. Okay, but the sequential scan would force us to remove the hotspot pages that are so valuable for these transactions, because we need to make space for the sequential scan of the pages of this really large table, all of which will only be used once, which is a real pity. Okay, so this is another scenario where LRU really doesn't shine. Maybe it's worth your time to pick a piece of pencil and paper and consider the effect that such a large scan has on a clock sweep operated circular array of buffer descriptors that you are tracing. So why not set up a small piece of paper with a circular buffer of 10 buffer descriptors, in which you can have these transactions operate on a small fragment of hotspot pages, like 3 or 4 pages, and then have another operation scan a table of like 20 pages and see how the clock sweep algorithm will react, and how the hotspot pages are actually being removed from the buffer, only to have these pages of the sequential scan inside the buffer, which are only used once. Okay. There are other page replacement heuristics beyond LRU. Maybe LRU is too simple, but it's implemented in a simple fashion. It's reliable and it works in many cases. But as you can imagine, a database architecture has developed quite a number of alternatives to LRU. For example, the variant LRUK, which not only considers the point in time when a particular page has been referenced, so that we can really find out which page has been least recently used, but it will also keep track of the K latest references. So not only the reference that is the last reference, but the K latest references. And the ability of the K latest references gives us the availability of these K latest references gives us the option to track of how frequent a page is actually being accessed. The frequency of the time that has passed between two subsequent accesses to the same page. The smaller this particular time span is, the more frequent a page is being accessed, and the more valuable it should appear to the database system. And LRUK is capable of tracking this frequency. So LRU tracks recency, LRUK tracks recency and frequency. And well, you can invest in the maintenance of this frequency information, of course, but the practice has shown that LRU2, so only keep the timestamp of the two latest references, is already quite capable of judging the frequency of accesses to a particular database page, factor this into the abstract value of such a page, and use that in clever decisions of which victim page to select. There is the sister strategy to LRU called MRU, which says that it's probably clever to replace the page that has been used just now. And this is the antithesis to LRU. So pages that have just been used now will probably not be of good value in the now coming future, and so should be replaced. And in a scenario where you have sequential scans that touch lots of pages but only touch these once during the scan, once the scan has passed the page, it has lost its value. For such scan heavy workloads, MRU doesn't seem to be the worst of replacement policies inside the database system. All right. And then there is, of course, the random strategy. Would just pick a a random victim from among the buffer descriptors. Of course, only among the unpinned buffer descriptors, that's for sure. This has a very straightforward implementation, needs no particular support of data structures and no maintenance, and could be a valuable strategy if the implementation is needed to be very compact, very simple, very tight. All right, and well, the rationales, I have just discussed them while we were going through this list here. So let's look at this particular scenario again, where the database buffer is at risk of being swamped by such a sequential scan and losing all its valuable content that would be of such high value to other transactions inside the database system. So PostgreSQL has some measures against such operations that would really swamp the database buffer with page references, bringing in pages that are maybe only used once at the cost of the removal of other high-value pages. Okay, and the variant that is implemented inside Postgres to remedy the situation is a variant of LRU that's based on a ring buffer. And the ring buffer is a strategy that should protect us from being swamped by large sequential scans. And that's, of course, in particularly very important if the buffer is small or if it's really busy, if lots of its slots have been occupied by hotspot pages, and being swamped by such a large sequential scan would be really hurtful. We would remove a lot of pages that are valuable to other transactions. To avoid this, PostgreSQL uses a so-called ring buffering strategy that is invoked every time the buffer is at risk at being swamped by large scans. And such a large scan might be just the scan we were mentioning in the second scenario in the slide before. So such a select from T sequential scan scenario where T is really large and the measure of PostgreSQL says a scan is large and is judged to be a swamping scan if it would occupy more than 1/4 of the size of our entire buffer. So if we would perform that scan and that scan would replace the content of 25% of all of our buffer pages, then that would be a swamping scan and should be handled by the ring buffering strategy. There are other scenarios inside the database operation which could lead to such swamping scans. For example, if we copy the contents of a table from a particular external file, that would bring in lots of data and that would populate this large table and would also lead to a swamp of the buffer. If we generate or create a new table, populate this record from a particular query, then all of the pages that are all of the results returned by this query would have to be brought inside the buffer because they make up the new contents of table T, and for large queries too, that might again swamp our buffer. Okay, alter operations on tables that touch a lot of records, maybe even all records, like append a particular column to all the rows of a table. If table T is large, that could affect lots and lots of pages, and bringing in all these pages would swamp the buffer. Okay, there's other operations like the vacuum operation inside the system that performs a visit of all pages of a database relation to see whether there is rows that could be removed because they are now obsolete and visible to all transactions that are currently going on. All of this would be considered operations that could swamp the buffer. If such a command swamps the buffer, we will not let it swamp the buffer, but only allocate a small ring buffer for this particular swamping operations. And that ring buffer will be a fraction of the buffer space. Only the ring buffer will only be allocated 1/8 of the overall size of the buffer. So 7/8 of the buffer will remain unaffected by the swamping operation. So in the ring buffer, we will load pages in the first page of the ring buffer, then the second, third. But when the ring buffer has been filled, we will just start at the top of the ring buffer again, overwriting pages that we have just read, under the assumption that we are performing sequential scan-like operations only, and that the value of pages that we have read a few pages before is indeed 0. So we would just walk inside that ring buffer, would replace pages in the ring buffer immediately without affecting any pages outside this particular ring buffer. And once the ring buffer, the swamping operation has been performed, all of the pages in the ring buffer would immediately be declared available for other buffer operations again. Because, again, as we assume, a sequential scan-like operation has been performed and the value of the pages in the ring buffer is low or even 0. So to finalize this particular video, it's running quite long already. It's 35 minutes. Okay, so let's see how this ring buffer behavior can be observed inside PostgreSQL. So let's switch over again here. Okay, so to simulate this behavior of PostgreSQL, to really bring it to action, we will artificially reduce the size of our buffer. It's 128 megabytes now. We will reduce it to 1 megabyte only now, so that even modest scan operations, modest sequential scan operations will be considered at risk of swamping that entire 1 megabyte buffer already. So let's do that. So let's stop the database server again. Stop you. All right. And then I will switch over to my PostgreSQL.conf configuration file here. As I told you, changing the size of the shared buffer is something that has to be performed while the server is down and will only take effect when the server is being restarted. Okay, so let's look for the shared buffer configuration variable. It's here. Shared buffers is 128 megabytes. Let's copy that and insert a new version here of just 1 megabyte. Comment this out and put a marker here so that I know, hey, this is something that really should be fixed when I start the server again after this video has finished. Okay. Right, so 1 megabyte of shared buffer, really super small. Any sequential scan will swamp that. Okay, so now let's restart the server again. Start. It will start with a 1 megabyte size of tiny buffer space now. So let's open the PostgreSQL shell and check the size of the buffer. It's indeed 1 megabyte only now. Okay. In 1 megabyte, there is not that many pages that will fit inside the buffer. So let's see how many pages are available in such a small buffer. That's only 128 pages. That's really super small. All right. Okay. So let's recall the ternary 100K table that you've already seen in the large experiment video, in the video before this. And let's recall that this table alone has more than 900 pages. So let's see. Yes. So it's stored in 75998 in this particular heap file, and it has 935 pages. A scan of this ternary 100K page, ternary 100K row table will indeed swamp a tiny buffer of only 128 pages. Hopelessly too small, the buffer to support a sequential scan here. All right. So currently, because we've just restarted the server, the buffer cache will be empty and will not be empty, but it will be empty regarding the ternary 100K table. Indeed, there is nothing in there. Currently, nothing is in there. We will change this now. We will now perform one of these swamping operations, a sequential scan of this humongous table, humongous from the viewpoint of the tiny buffer of 1 megabyte. And we will, of course, indeed perform this operation, and we will write the protocol of all the buffer hits and misses that have occurred while this sequential scan is being performed. And of course, because the buffer has been empty regarding ternary 100K, we will see 935 buffer misses here. All right, that's what we see. 935 buffer misses have been observed for this sequential scan. Okay, so now that the swamping scan has been performed, will all of the 128 pages of the buffer be in use by the ternary 100K relation? Or will the majority of the buffer been used for that? Everything else has been removed and declared victim? So let's see. Let's check how the content of the buffer cache now looks like. Okay, that's only 13 rows. Only 13 rows. Okay, that's not 120, it's way less. It's even less than 1/8 of the ring buffer size that we were promising. And that's because in the meantime, while I was performing the scan and then talking and then performing this particular command, some of the pages of the ring buffer, of the 16-page ring buffer, have already been reclaimed by the buffer. 13 of these are still present in the buffer. Some of these, 3 of these, have already reclaimed for other, probably more valuable operations. As you can see, all of these pages in the ring buffer are not dirty because this has been a sequential scan read-only operation. The usage count has already been decreased down to 0. The usage count has been 1 when we were using the pages in the ring buffer, but probably some clock sweep rounds have been performed in the meantime. The usage count has been brought down to 0, and nobody will bring the usage count of these pages back up again. Nobody's interested in these pages currently. So over time, these pages will be removed from the buffer and reclaimed by something that is more valuable. So we were saved from really swamping the buffer with 935 pages. We couldn't fit them anyway, but the whole scan was confined into a ring buffer that in the beginning only occupied 16 pages. Only 13 of them are present here. And you can see that this has indeed been performed in terms of a ring buffer operation. You see that the heap file page 919 has been loaded in this particular slot, 920, 927, and then the end of the ring buffer has been reached, and we start again at the top of the ring buffer where the next few pages have been located. 934 is the last page of the heap file scan. So indeed, this has been the pages of the sequential scan have been brought in the ring buffer fashion, and the buffer has protected itself from being swamped. So let's see if anything is still. Oh, okay, it's less pages are still remaining from this buffer scan. All of this of these very invaluable pages at this particular point in time will be gone in a good while. So let's perform a new scan. Let's perform a new scan of the ternary 100K relation. In the meantime, all of this had to be brought in fresh from the secondary storage. Another scan and another scan. Okay, now I'm seeing what I wanted to show. So the 2 last scans have been following each other in a quite rapid fashion, so that the second scan was lucky and found the 16 last pages of the last scan still in the ring buffer. So we could benefit from these 16 pages, but had to bring in all the 919 other pages, which were then placed in the ring buffer. Okay, so and this only reminds me of resetting the shared buffer value in the PostgreSQL conf file. I will do this, but I will do this once this video is over. Thank you for your interest. This concludes the discussion for now of the PostgreSQL buffering strategy. There is more to be said about buffering and caching when it comes to MongoDB, but this would be a topic for the next video. See you then.